So in part C, we are told that the satellite is moved to a new circular orbit. Radius increases by 2 kilometers. We need to outline why the magnitude of the field strength at the new orbit is approximately the same as the old orbit. And well, it is because the change in the orbital radius is very small. So if we compare it to the distance it is orbiting at, it is much smaller than 10 to the 7 meters, which would be 10 to the 4 kilometers. So the change is way too small. So there's a very small change in potential as well. If we look at the graph, so there's a very small change in the radius and the field strength as well, therefore. And in part 2, we are told to determine the change in total energy of the satellite. So we know the total energy is made up of 2 components, kinetic and potential energy. So we need to consider that the potential energy, the change in the potential energy will be equal to mg times delta H. So we can calculate this 750 times 4, not 9.81, because the g at this height is 4, times 2 times 10 to the 3. This will give us 6 times 10 to the 6 joules. And we also know that the kinetic energy is equal to the minus change in potential energy over 2. If we think back to the energy graphs, we remember that the kinetic energy was here, potential energy was here, total energy was here. And from this we can remember that the equations of the energies was that we had kinetic energy and the potential energy was the same, only with a 1/2 multiplier. So this is important to remember. And so if we plug this in, we will simply get minus 3 times 10 to the 6 joules. So the change in the total energy is the sum of the change in potential and kinetic energies. So 6 minus 3 is going to be 3 times 10 to the 6 joules. And therefore, that is going to be the total change in energy.